with section 5.3, we move on to annuities. Now we're going to start by focusing on ordinary annuities. I want to point out that on your formula sheet that you will have provided for you on the test, we've covered our simple interest, our compound interest, interest compounded continuously, at effective rate or APY, and we're moving down here. Now these two payment formulas we're not going to get to quite yet. We are at ordinary annuities today. Future value, present value, and then annuities due, future value, present value. I think that we actually cover, well, we'll see. Let's work through and see what all we cover today in 5.3. Okay, this is different from the loans and investments that we studied in the first two sections of Chapter 5. Those investments start with a single lump sum, and then that's it. You're either borrowing a certain amount or you are investing a certain amount, and then you just wait to see what interest happens. Payments are not made periodically on these loans and investments that we've been talking about. Now that we've moved on to annuities, we are talking about making a sequence of payments. An annuity you pay into over time. You make equal amounts of payments paid at equal periods of time, and these may be to accumulate funds, or they may be to pay out funds. For example, if you have ever known anyone who's gotten some kind of a settlement, like an insurance settlement, say in a car wreck, and they get insurance money, and then they are told that as part of that they won't get it in a lump sum. They'll get a certain amount of money every month for a certain period of time. Well, then the insurance is going to pay into an annuity to make sure that they have funded those settlements. Something like that. That would be how you would pay out funds. Or if you know anyone who has a trust fund that gets payments out of it. All right, we're going to start with ordinary annuities. Now, an ordinary annuity, payments are made at the end of each pay period. Whether that's monthly, quarterly, semi-annually, annually, whatever it is, the payments are put into the annuity at the end of the period. The frequency of the payments is going to be the same as the frequency of the compounding term. So if you are paying in monthly, interest is being compounded monthly. If you're paying in quarterly, interest is being compounded quarterly. So we are looking at future value of an ordinary annuity. Again, we've got future value out here. This is if you keep doing the payments like they're scheduled, this is what you will have at the end of however many years. And we just kind of ignore this one. This is if you have a finance type calculator, but all our regular calculators, we're going to be using this formula. Ordinary annuity payment at the end of the period. I is still R over M. That's not new. Interest rate per period. R is the annual interest rate, M is the number of periods per year, and N is the total number of periods. So N is still M times T. So the compounding period times the number of years. Okay, let's do an example. Calculator math, you've got to make sure that you identify what you know and what you need. Write down your formula. I want to see that formula written down, and then do your calculations in your calculator. A rookie in the National Football League just signed his first 7-year contract. To prepare for his future, he deposits $350,000 at the end of each year for 7 years in an account paying 4.1% compounded annually, and we want to know how much he's going to have on deposit after 7 years. So this is not just an investment, a standard investment, because he is making yearly payments at the end of each year. So end of each year lets us know it's an ordinary annuity. 7 years, that's T. 4.1%, that's R. Compounded annually, that's M. How much will he have after 7 years? So we're looking for our future value. We're going to be using our ordinary annuity future value formula. I'm going to go ahead and write it down here. You've got to make sure that you have the formula copied down correctly, that you choose the correct formula, copy it down correctly, and then fill everything in appropriately. So our payment, well, he's paying in $350,000. That's his annual payment. then we've got all of this inside this rational expression. So we have I and we have N. I is still R over M, and N is still M times T. So my rate is 4.1%, becomes 0.041. M compounded annually, that's just 1, so that makes this problem simpler. And then N, the number of total compounding periods, is just going to be 7 because it's being compounded annually. So I start filling in inside my brackets. I've got 1 plus I, 0.041 to the nth power minus 1 over I. Now, this one's simplified a bit because our compounding period is 1. It's being compounded annually. When we plug this into our calculator, I still really recommend that you work from the inside out, that you don't trust too much that your calculator is going to get that correct order of operations without you doing a little bit of help. So I'm going to start inside my parentheses. Now right here, 1 plus 0.041, that's just 1.041. Since that is just over 1 here, that simplifies that down. I need to raise that to the 7th power. And then before I do anything else, I subtract 1 from that. That's my numerator. Then I divide it by my denominator. That's what's going on inside these brackets. And the last step is always to multiply it by, we have been multiplying by the principal, now we're multiplying by the payment. And we see that we get a really large amount at the end of those 7 years, which makes sense because we're paying in $350,000 every year. So at the end of the 7 years, we've got $2,772,807, and rounded to the nearest penny, that's going to be 59 cents. So that's the total in the account, the future value at the end of 7 years. Now let's think about what that is comprised of, what that's made up of. Well, how much did this NFL player invest? He invested $350,000 a year for 7 years. So $350 times 7, he invested $2,450,000. So out of this $2,772,000, almost $73,000, he invested $2,450,000 of it out of what his paycheck was, what he was getting. That means that the interest that he earned is the difference between what he invested and what he ended up with. So if I subtract these two totals, I find out that he earned $322,807.59 of interest, which that's almost another year's worth of investment. And he's still got almost $3 million that he wouldn't have had if he just spent it all. Okay, let's look at the next one. We're going to look at a sinking fund. A sinking fund is set up to receive periodic payments. It's a type of annuity, such as when a corporation or a municipality sets up a fund to repay a bond issue. Now, the thing you need to remember about a sinking fund is that it is a type of ordinary annuity. So when you are, I can't spell today. Let's just start that one over. So when you are reading the problems and it labels something as sinking fund, you automatically know that you're going for your ordinary annuity formulas. Ordinary annuity, not annuity due. So we're looking at ordinary annuity. Now, when would you need a sinking fund? Let's say that you have a business and your business is making t-shirts, printing t-shirts, and you know that after a certain amount of time your machinery is going to wear out. You're going to have to replace it. Well, instead of waiting until it breaks and trying to come up with all the money, you set up a sinking fund so that you're going to be able to pay it, have everything that you need to pay for the new machinery at the end. A business sets up a sinking fund so that it will be able to pay off bonds it has issued when they mature. If it deposits $12,000 at the end of each quarter in an account that earns 5.2% interest compounded quarterly, how much will be in the sinking fund after 10 years? So what do we know? What are we finding? We've got a sinking fund, so we know it's an ordinary annuity. Our deposit amount, our payment amount is $12,000. End of each quarter. Quarter is our compounding period. An account that earns 5.2% interest. Now, they're making quarterly payments, so we're going to assume that interest was also compounded quarterly if we hadn't been told that. And they are leaving it for 10 years. How much will be in the sinking fund? Well, that's the future value. So for our formula, we're going to need I, which is R over M. In this case, 0.052 over 4. And then N is M times T, which is going to be 4 times 10, or 40. Those are pieces of information we're going to need for our formula, for our calculations. Now notice that I don't ever plug this in and round that off, because you don't round till the end. If you round before the end, you're going to just affect your result. So I set up my ordinary annuity formula based off of my formula sheet or my first page of notes, whichever way you want to look at it. My payment here is $12,000. In parentheses, I have 1 plus that value I that we set up here, raised to the n power, which we calculated to be 40, minus 1, don't forget your minus 1 in the numerator, over I. Make sure you write this down. Then when you plug this in to do in your calculator, when I set this up, again, I'm not going to trust order of operations to my calculator. I'm going to make sure I do it in the right order. My numerator divided by my denominator here, and then plus 1 is what's inside my parentheses. I raise that to the 40th power, and then I subtract 1. That's my numerator overall. I need to take this value and divide it by, in parentheses, because my denominator now has a numerator and a denominator, a little rational expression there, 0.052 divided by 4. That's what is inside my brackets, and I'm going to multiply that times my payment value. This is what I get as the worth of the sinking fund at the end of those 10 years. I'm going to round it to 81 cents. $624,369.81. What if I wanted to know how much of that they actually invested and how much was interest? Well, they made payments of $12,000. How many payments did they make? Well, they made 40 payments of $12,000. So out of this total $624,000, $480,000 of it was what they paid in. So if I subtract that from the total in the sinking fund, I find that they earned $144,369.81 in interest. Alright, another example. A firm borrows $6 million to build a small factory. So they're going to have to pay back this $6 million. The bank requires it to set up a $200,000 sinking fund to replace the roof after 15 years. Now this makes sense. So the bank loans them $6 million to build this factory, but it knows that it wants to make sure that they can pay off this loan. And so as part of the terms of the loan, they require building maintenance to be factored in. So it requires them to set up a sinking fund to make sure that they're going to be able to replace the roof when it's needed in 15 years. The firm deposits, if the firm's deposits earn 6% interest compounded annually, find the payment it needs to make at the end of each year into the sinking fund. So what do we know and what do we need to know? We've got different information here. So the $6 million is not part of our calculations. This is what we need the future value of our sinking fund to be. Here we've got our rate. Compounded annually is the compounding period. We're looking for our payment. That's our unknown. We're looking for our payment. 15 years, that's our time t. Okay, so I is going to be that rate, 0.06 over 1, so just 0.06. M is t, which is 15, times, not m, n is t times, that's what threw me, but that doesn't look right. So my number of compounding periods, since it's just compounded annually, it's just 15 compounding periods. So I'm using my ordinary annuity future value formula. It's just that what I know is the future value. What I'm solving for is going to be the payment. So what I'm going to end up needing to do is divide the future value by all of this. So I could go ahead and move that over there and set it up, or I could set it up differently and move it at the end. I think we'll go ahead and set it up like we're used to seeing it, and then divide at the end. So I need to end up with $200,000. I don't know my payment, but I do know everything that goes inside these brackets. I've got 1 plus 0.06 to the 15th power minus 1 over 0.06. Now to solve for payment, I'm going to divide both sides by all of this. So my payment is equal to that 200,000, the future value of the sinking fund, divided by this bracket setup. Well, 1 plus 0.06 is 1.06 raised to the 15th power minus 1 over 0.06. Now when I plug this, you get to choose how you plug this into your calculator. Make sure that the way you do it, the order you do things, is getting you to be correct every time when you do it. So I'm going to start with the more complex piece, this denominator, and I'm going to do 1.06 to the 15th power, then subtract 1 from that, and divide it by, let me try that again, 1.06 to the 15th power. Yep, there we go, minus 1. Divide it by 0.06. Okay, this is what I need to divide that 200,000 by. So I've got to start with my numerator, 200,000. Divided by, and then I'm going to use that second answer function to bring up my denominator. And this is the size of the payment. Round to the nearest penny would be 55 cents. So their payment that they need to make annually into the sinking fund to make sure that they have enough is $8,592.55. So that's how much they need to pay into the sinking fund every year. All right, annuities due. Annuities due. So we're switching to our other set of formulas, our last two formulas here at the bottom of our sheet. Annuities due, future value and present value. Notice we're just focusing on future value today. Annuities due are when payments are made at the beginning of each period. So before they start calculating things, you're making the payment. Now, how does that change our formula? Well, notice that it's got a couple of different pieces. You've got n plus 1 as your exponent here, and then once you find this, you subtract a payment. So those are the two things that are different. The payment is made at the beginning of each period when it's an annuity due. I is still R over M. N is still M times T. But our exponent is n plus 1. So you've got to make sure that you adjust that exponent and that you subtract out one payment. Okay, let's do a couple of examples and then we'll be done with this section. Find the future value of the annuity due at the given rate. So that tells you right off the bat. We've got annuity due, so we know which formula we're going to be using. We're finding future value. So future value of an annuity due, payment times, and then I subtract a payment at the end. In here I've got 1 plus I to the n plus 1 as the exponent minus 1 over I. We've got our payment amount. We've got our time at 8 years. We've got our rate. Ooh, tiny rate. That's not much interest at all. Compounded annually. There's our value M. So I will be if I change this percent to a decimal, 0.0021 compounded annually is just over 1. N is going to be m times t, so 8 times 1 is just 8. My exponent, however, is n plus 1, so that's going to be my exponent. It's 9. Okay, let's fill in what we know. We're solving for future value. We know our payment. Our payment is $1,050. And when we get done, we're going to subtract a payment. So that's part of our formula. Inside we have 1 plus, and then that's just over 1, so I can just write 0021. My exponent is 9 because it's n plus 1, minus 1 over that 0.0021. Okay, order of operations, 1.0021 to the 9th power. Then I subtract my 1. I divide that by my denominator. Then I take this value of my brackets and I multiply by my payment, because multiplication comes before subtraction. So I'm going to multiply this value in my calculator times the payment of $1,050. And then because it's an annuity due, not an ordinary annuity, I still have to subtract one payment. So the amount in the annuity, the future value after 8 years, is going to be $8,479.77. Out of that, how much did they pay in, how much was invested, and how much was interest? Well, because we made end up subtracting that payment at the end, we don't use 9 as the number of payments. You use 8 as the number of payments. So you do 1,050 times 8, which is 8,400. And the difference right there between the total in the annuity and the amount invested is just $79.77. Does that make sense? That's not a lot of interest for 8 years, right? Well, yes, because my interest rate was tiny. It's less than 0.5%. It's just 0.21%. Okay. Now this next one I had to work on a little bit to make sure that I got it right. This one is an annuity due. A mother opened an investment account for her son on the day he was born, investing $1,000. So payment up front at the beginning. Each year on his birthday, she deposits another $1,000, making the last deposit on his 18th birthday. If the account paid a return rate of 5.6% compounded annually, how much is the account at the end of the day on her son's 18th birthday? So we've got our payment amount, we've got the number of years, we've got our compounding period, we've got our rate, and we made the payment up front, so we've got an annuity due. So we know which formula we're going to set up. I is going to be 0.056 divided by 1 because they're annual payments compounded annually. That's actually, nope, that was right. That was T. Not N, that was T. There we go. That's what I did wrong. 18 is the number of years, so that's T. N is M times T. So 1 times 18, just 18. N plus 1, my exponent is 19. So on his 18th birthday, they make the 19th deposit. Alright, so let's set it up. Our future value of our annuity due, we're making those $1,000 deposits. We're going to have to subtract out a deposit at the end. Inside parentheses, we've got 1 plus 0.056 raised to the 19th power because it's n plus 1 minus 1 over 0.06, that value I. Work inside your parentheses first, then multiply by the 1,000, and then finally subtract out that 1,000. So the future value of that annuity is $31,426.46. Now, the thing is, today is his 18th birthday, right? So today, she made her 19th deposit. So on his 18th birthday, that's the 19th deposit, because the first deposit was made at 0 years, right? So this is for 18 of those deposits. We need to go ahead and add back in that $1,000. So as long as she goes ahead and pays that $1,000 on his 18th birthday, like it says, we're going to add that back in. That's how much is in his account on his 18th birthday. Okay, that's it.